In this video, we will continue looking at the trend in first ionization energy across a period, and we will examine the anomalies and explain them. On my screen, you're going to see two images. The two images will show first ionization energy across a period. The top image shows how first ionization energy changes across period 2, and the second image, the one below, shows how it changes across period 3. We will of course first establish our general trend, and our general trend is across a period first ionization energy increases. If we look to our two images, we are going to see some exceptions to this rule, and the exceptions occur between a pair of elements. So for example, across period 2, there's a decrease in first ionization energy between beryllium and boron, and nitrogen and oxygen. And across period 3, we also have a decrease in first ionization energy from magnesium to aluminum and phosphorus to sulfur. We are going to examine these decreases in first ionization energy by taking a look at these pairs of elements as they would appear in the periodic table. Meaning, we're going to compare the decrease in first ionization energy from beryllium to boron and magnesium to aluminum, as the same reason would explain these decreases. So this is why I have beryllium and boron together and magnesium and aluminum. We will also look at nitrogen and oxygen and phosphorus and sulfur in terms of their decreases, as they also appear above and below each other in a group. Right, so nitrogen is above phosphorus, oxygen is above sulfur in a group. In order for us to understand why there are decreases in this first ionization energy, we must understand that first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions with a single positive charge. This electron that we are removing will be from the valence or outermost shell of each atom. We have looked at electronic configuration, so we can identify which orbital the electron is being removed from, or at least the subshell where the electron is to be removed from. So I'm going to go ahead and write in the electronic configurations for our elements, and we will then look at the electronic configuration to figure out why there's a decrease in this first ionization energy. I have written in the electronic configurations of the respective elements, and we're going to compare them as pairs of elements, and we will look at the reasons why that first ionization energy decreases when we would expect an increase. So let's compare beryllium to boron, where in beryllium we would be removing an electron from a filled s orbital versus boron, where we would be removing an electron from a p orbital. If you look at magnesium and aluminum, it's the same, where in magnesium we would be removing an electron from a full s orbital versus removing an electron from a p orbital. We would expect an increase in first ionization energy across a period, meaning that more energy is required to remove the electron from the outermost shell as we move across a period. So why does it take less energy between beryllium and boron and magnesium and aluminum? We can very easily summarize it by saying less energy is required to remove an electron from, I'm just going to use p orbital here, from a p orbital, right, versus a filled s orbital. And this is because p orbitals are higher in energy than our s orbitals, meaning that they are further away from the nucleus. So therefore, less energy would be required to remove an electron from a p orbital. Right, so it's a higher energy level. So you can think of it like this, in that the p orbital is a higher energy level, less energy is required to remove an electron because that orbital is further away from the nucleus. Or you can think of it as it takes extra energy or extra energy is required to remove an electron from a full s orbital. Right, so either answer will work here. If you say the p orbital is higher in energy, or it's a higher energy level, less energy is required to remove an electron from that p orbital. Or if you say more energy is needed to remove an electron from a full s orbital compared to a single electron in a p orbital, either answer will work here. So this is why it takes, or the ionization energy drops from beryllium to boron, magnesium to aluminum. Less energy is needed to remove an electron from a higher energy level p orbital, or more energy is needed to remove an electron from a full s orbital. Let's talk about nitrogen and oxygen and phosphorus and sulfur. If we look at the electron being removed from nitrogen to oxygen, and even phosphorus to sulfur, right? So an electron is being removed from a half filled p subshell for both nitrogen or phosphorus versus a p subshell which contains 4 electrons. So I just want to come across here and draw what this p4 subshell would look like. So we would have 3 electrons filled in of equal spins, and the 4th electron would spin pair. The electron which we are removing from that p4 subshell would be from the spin pair. Right, so comparing this to sulfur, we would be removing an electron from a spin pair. Let us look at why it takes less energy to remove an electron from a spin pair, that is sulfur or oxygen, compared to a half-filled orbital, half-filled p subshell of either nitrogen or phosphorus. We have already covered that half-filled or completely filled subshells are more stable than incompletely filled subshells. Right, so we can state our answer in 2 ways here, which is that a half-filled subshell is stable. Right, so that means it's stable. So to remove an electron will take a certain amount of energy, keeping in mind that that half-filled subshell is stable. It means, why does that indicate to us or tell us that it takes less energy to remove an electron from an incompletely filled subshell? Our half-filled subshell is stable because all the electrons are of equal spins, right? Compare this to our p4 subshell, where we have a spin pair. This means less energy is required to remove an electron from a spin pair, and this is because of spin pair repulsion. Now I'll explain what spin pair repulsion means. It refers to that mutual negative repulsion between electrons, right? Or mutual negative repulsion between an electron pair. Where we have a spin pair, it took energy to put the 2 electrons of opposite spins together. So therefore, it's going to take less energy to pull away 2 electrons which are both negatively charged. And this is because of their mutual negative repulsion. So it's taken less energy to remove an electron from a spin pair due to spin pair repulsion versus removing an electron from a half-filled subshell, which is already stable. Right, so you can use both answers or the combination of the explanation of that half-filled subshell being stable and saying that it's easy to remove an electron from a spin pair due to its spin pair repulsion in order to answer a question which may be explain why first ionization energy decreases from nitrogen to oxygen or phosphorus to sulfur. So this here is our answer. Right, so thanks for watching. Keep tuned for more videos.